All right, let's dive in. We're going to take a journey, a really big one, from a violent cosmic birth all the way to an almost eternal death. We're talking about the complete life cycle of one of the most extreme, most captivating objects in the entire universe, the black hole.
So right off the bat, let's tackle the big question, the one that sounds like it's straight out of a movie. How does the universe's most extreme object die? I mean, think about it. How can something with supposedly infinite density, a place that not even light can escape from, just cease to exist? Well, the answer is one of the weirdest, most fascinating stories in all of physics, and we're going to unpack it.
Okay, but before we get to the end, we've got to start at the beginning, right? And for a black hole, the beginning, it's not quiet. It's an incredibly violent, spectacular affair. It all kicks off with the death of a truly gigantic star. And when I say gigantic, I'm not kidding. We're talking about stars that are at least 20 times more massive than our own sun. That's the minimum requirement, the entry ticket to this cosmic club. Only the absolute heavyweights of the universe get to become black holes. You see, for its entire life, we're talking millions, maybe billions of years, a star is locked in this epic tug-of-war. On one side, you've got gravity, just relentlessly trying to crush it inward. And on the other side, you have the nuclear fusion in its core, which acts like a furnace, creating this massive outward pressure pushing back. This perfect, delicate balance is what keeps a star stable. But that balance can't last forever. Eventually, the star starts making iron in its core. And here's the problem. Fusing iron doesn't create energy. It actually sucks energy in. So that outward push from the furnace, it just stops. And in that split second, the tug-of-war is over. Gravity wins, instantly. The core collapses in on itself so fast, it triggers one of the most powerful explosions in the universe, a supernova. And after all that chaos, what's left behind is the tiny, hyperdense seed of a new black hole. And that seed, we call it a singularity. And honestly, this is where things get really, really weird. I mean, this is the point where physics as we know it just completely throws its hands up and says, I don't know. Imagine taking all the mass from the core of that giant star and squishing it down into a point with literally zero volume and infinite density. It's a place where our two best theories of the universe, Einstein's gravity and quantum mechanics, just clash, and neither one has the final say. So, okay, we've got this impossible point of infinite density, but that's not actually what we see or interact with. What really defines a black hole, its most famous feature, is its boundary. That infamous point of no return we call the event horizon. Now, it's super important to remember this. The event horizon isn't a physical thing. You couldn't, stand on it or touch it. It's more like a mathematical line drawn in space-time. It marks the exact spot where gravity becomes so ridiculously strong that the speed you'd need to escape, the escape velocity, is faster than the speed of light. And since we know nothing can break that cosmic speed limit, once you cross that line, that's it. You're not coming back. This brings us to how these things actually behave. And let's be honest, there are a ton of myths out there. So what's it really like to live near a black hole? What's the reality? Okay, let's clear up the biggest misconception right now. Black holes are not cosmic vacuum cleaners. They don't just go roaming around the galaxy, sucking things up like a Hoover. The reality is much simpler. They're just objects with a whole lot of gravity. They obey the same rules as everything else. If you stay a safe distance away, you can orbit one just like you'd orbit a star. It's only when you get too close that things get complicated. Here's a thought experiment that really drives this point home. Imagine, right now, our sun was magically replaced by a black hole with the exact same mass. What would happen to Earth? Well, nothing, orbit-wise. We'd keep going around it just like we are now. Now, don't get me wrong, we'd freeze to death pretty quickly, but we wouldn't get sucked in. And that's because gravity only cares about two things, mass and distance. It doesn't care what the object actually is. But what if you do get too close? What happens then? Well, you experience something with the best name in all of astrophysics, spaghettification. Seriously, the pull of gravity at your feet would be so much stronger than the pull at your head that the tidal forces would literally stretch you out, like a noodle, into a long, thin stream of atoms. A pretty gruesome end before you even get anywhere near the center. All right, so a black hole's born in a supernova. It lives its life as this massive anchor of gravity. But that brings us back to our original question. How does it die? To answer that, we have to leave the familiar world of Einstein's gravity behind and take a deep dive into the truly bizarre realm of quantum mechanics. Because it turns out black holes aren't completely 100% black. The legendary Stephen Hawking figured out that they actually very, very slowly leak. They radiate energy back out into space. And this isn't about gravity at all, it's a quantum effect. Think of it like a tiny, constant quantum heist happening right at the edge of the event horizon.
So how does this heist even work? Get ready, because this is where it gets strange. In the quantum world, empty space isn't really empty. It's constantly fizzing with pairs of virtual particles that pop into existence and then immediately cancel each other out. They're there and gone in a flash. But what if a pair of these particles pops into existence right on the edge of the event horizon? One particle might fall in, but its partner could escape out into space. Now, the universe has a problem. A free particle just appeared out of nowhere. To balance the energy books, the black hole has to pay the price. It loses a tiny, tiny bit of its own mass and energy.
Now, when I say this process is slow, I mean it's impossibly slow. For a black hole that's just the mass of our sun to evaporate completely, it would take 10 to the 67th power years. That's a 1 with 67 zeros after it. Let me put that in perspective for you. The universe itself is only about 13.8 billion years old. We're talking about a timescale that is so vast, it's almost meaningless to our brains. And there it is, the whole shebang, the complete life cycle. A violent birth in the heart of a supernova, a long, long life as an anchor of gravity shaping galaxies, and then a quiet, impossibly slow death driven by the weirdness of quantum physics until it all ends in a final, tiny burst of energy. But this whole story, it leaves us with one last massive, mind-bending puzzle that physicists are still tearing their hair out over. See, there's a fundamental rule in physics that says information can never, ever be destroyed. So what happens to the information about every single thing that ever fell into the black hole? When the black hole finally evaporates and vanishes, where does all that information go? No one knows for sure. And finding the answer, well, that could completely change everything we think we know about the universe.